Hello, honors physics students. Let's go back to problem number 1 and take this from a vector perspective. So in problem 1, we had the baseball coming in and it was hit back, and we found the change of momentum. And of course, we write change of momentum as Pf minus P naught, which of course we did. But now let's rearrange this to solve for Pf. Adding P naught to both sides, we write Pf equals P naught plus delta P. That should make sense, right? The final momentum is the initial momentum plus the change of momentum. Sure. But now let's consider this to be a vector equation. This says that if you take the vector of the initial momentum and add the vector of the change of momentum, you'll get the vector of the final momentum. Well, that's a vector equation. That's like a vector addition. So let's draw this out as a vector diagram. Ooh, we haven't done that in a while. So the initial momentum was pointing east. So this could represent the initial momentum of positive 2.1 kilogram meters per second, or 2.1 kilogram meters per second in the east direction. In letter B, we calculated the final momentum, which according to our vector equation is actually the resultant, right? The final momentum is pointing back west of an equal size compared to P naught. And so here's Pf. Notice I'm drawing them tail to tail because really this is the resultant, right? The resultant is always drawn from the tail to the first towards the head of the last. We haven't actually drawn the second vector because the second vector is actually delta P, right? P naught plus delta P. Well, we see delta P was negative 4.2. What does the negative mean? Well, we called east positive. That means the negative sign means west. And so here is delta P. And now we can see this looks like a normal vector diagram. The first vector, P naught. Here's our tail to head connection. Our second vector, delta P. And of course, we draw the vectors to scale. Delta P is twice as long as P naught. And this makes everything make sense, so that the magnitudes of P naught and Pf are the same value. And so here's a vector diagram, a visual representation of what happened. The baseball came in going east. When you hit it, we gave a change of momentum back west, enough not just to stop the baseball, but to send it back on its way with a momentum that was equal in magnitude to the original momentum, but in the opposite direction. And so I always like to try to draw the vectors here to help us visualize what's happening. Some students like that better than just the math and the equations. Let's take a look at problem 2. This is where you were either stopping the car by applying the brakes or by hitting the brick wall. And when you responded to my questions about letters C and D, we should have recognized that, of course, hitting the brakes is better for your safety. The force is clearly less than it would be when you hit the brick wall. But what about the different impulses? Well, impulse, remember, is change of momentum. And we calculated the change of momentum. It's the numerator of the fraction. It was the 63 kilograms times 0 minus 24. And here we hit the wall. It's also 63 kilograms times 0 minus 24, which means that no matter what, you went through the same change of momentum. Well, of course you did, right? No matter what, you came in at 24 meters per second, and no matter what, you were going to stop. Whether you hit the brick wall or you apply the brakes, you're going to stop. You're going to have lost all your momentum. Impulse is change of momentum, which means that no matter which process you go through, you're going to be going through the same change of momentum. You'll get the same impulse on you. So this is a situation that can be described by the term known as give. In physics, we define give, or we use the term give, when we're comparing collisions. Collisions that have the identical initial and final conditions. That's like this situation of stopping the car. No matter what, you're coming in at 24 meters per second, and no matter what, you're going to end up with a final speed of 0 meters per second. So in both situations, we have the same initial and final conditions. So when we compare these collisions, where initial and final conditions are identical, the one that extends the time, we say, has more give to it. Which situation would that be in terms of stopping the car? Is that hitting the brakes or hitting the wall? Well, hitting the brakes had a longer amount of time, 5 seconds versus 0.005 seconds. That means that hitting the brakes has more give to it. But no matter what, your change of momentum and your net impulse have to be the same. So we can show that with the graphical interpretation of the equation by showing this, that no matter what, you're going to have a certain change of momentum or certain net impulse on you. You can get that with a large net force through a short amount of time, or a small amount of net force extended through a longer change in time. Again, the situation that extends time is the one with more give. This is applying the brakes. Applying the brakes over 5 seconds reduced the force down to 300 newtons. 300 newtons is not that bad. You know, that's the weight of maybe a 30-kilogram person. Maybe like if your little brother or sister was sitting on your lap, that'd be a force of 300 newtons. A little uncomfortable, maybe, but nothing bad. The one where you hit the wall, that force of 300,000 newtons, well, that's something that your body actually couldn't withstand. Your bones would be ground to dust, your organs will pulverize. The human body cannot withstand 300,000 newtons. That's very little give to it. Now, hopefully, in between, even if you do hit the brick wall, you're wearing your seatbelt. The seatbelt would stop you in a time of, maybe 0.1 seconds, 0.01 seconds, to the point where it's still going to be a large amount of force, but it's something that your body can withstand. And this is why you wear seatbelts. This is why we also have airbags. If you were to hit the airbag, there's a lot of give to it, and so it would slow you down in a longer amount of time, applying less force to you as opposed to you hitting your steering wheel or hitting the dashboard or hitting the windshield. We have all these safety measures because they have more give. They extend the time, and thereby they decrease the amount of force to slow you down. The term give can sometimes be confused with another term, which we'll identify here as follow-through. Now here's a term you're probably familiar with. This appears a lot of times in sports or maybe in gym class. Your coach tells you to follow through. For example, in tennis, you need to follow through on your serve. In basketball, you need to follow through on your shots. In baseball, you need to follow through with your swing. And here, it's not just a mental thing, it's actually a physical thing. When you follow through on something, you're extending the contact time. And as a result, you increase the impulse. So your coach is not just telling you a mental thing. When you follow through on your swing or your kick or your throw, whatever it is, you're actually pushing for a longer amount of time. Impulse, or net impulse, is net force times delta t. And so when you follow through, even if you don't increase the amount of force you use, you are increasing the amount of time you're applying that force. And so you're going to necessarily get a larger net impulse. Net impulse translates into change of momentum. In this way, you're going to send the ball or the puck or the javelin, if you're throwing it, whatever it is, faster, farther, towards the goal, past your defender, whatever it is. And so when you increase the contact time, you're always going to be increasing the impulse. Now, give and follow through can be confused with each other because both deal with an increase in time. You just have to be very, very careful. In give, no matter what, the delta p, or the net impulse, will stay the same. Right? In a collision, no matter what, you're going to come to rest. You're going to lose all of your momentum, so the net impulse on you will always be the same. Changing the time, therefore, changes the force. But in follow-through, you're changing the time to specifically change the impulse. These are just not the same thing, and the more you look at them, hopefully the clearer it becomes. So one last note of our problems 1 and 2. In both of them, we found the net force by manipulating the impulse and momentum equations to say sigma f equals delta p over delta t. Well, it turns out this version of the equations has historical significance. If you were to go back to Newton's original works when he wrote his laws, he never actually wrote sigma f equals ma. I know, I'm living a lie, because when he was doing his experiments, he didn't really measure objects' acceleration. Instead, he measured what he called a quantity of motion, which we now interpret to be momentum. So he was actually studying changes of momentum, which means that sigma f equals delta p over delta t is actually closer to the way Newton originally wrote his second law. Now, he wrote it using calculus notation, so a better version of it would look like this. Sigma f equals dp over dt, or as we say it, dp dt, or the first time derivative of momentum. And it's okay if you don't know what that means or recognize this notation, but eventually when you get to calculus, you'll see this. This is really the way Newton originally wrote his second law.